Hey, pre-calc. So this is 7.2, the inverse trigonometric functions continue. So example 1, find the exact value. Remember we talked about the exact value being you may not use your calculator, okay? Anytime the instruction said exact value, it means no calculator. Whoops, what's happening? With that said, A, find the exact value of sine composed with tangent inverse of 1/2. Now let's talk about, I'm going to change up my pen color. Oh, if it lets me. So from section 7.1, the first thing we want to do is complete the inner component. So tangent inverse of 1/2. Now this should be a review from the last unit, okay? It's gonna equal to some angle. We don't know what angle that is. So this whole thing can technically turn to some unknown angle. Well, there are two ways to go about this. I'm gonna show you the first way. The first way is if you know exactly what that angle is, and sometimes you may, okay, then you can give me the angle right away, and then we would go and find, okay, sine of that angle will give us the final answer. But in this case, tangent inverse of 1/2 is not an angle that you know without using a calculator. So the first thing we want to do is check for restriction. Tangent inverse is restricted in quads 1 and 4. Now, because it is a positive 1/2, we know this angle will come from quadrant number 1. So what we want to do is draw a triangle. Whatever this angle is, we don't know. We're trying to find out. It doesn't really matter. But we do know, right, if we were to compose both sides by tangent like this, would you agree tangent of some unknown angle is going to be 1/2? Well, tangent is going to be opposite over adjacent. So using Pythagorean theorem, a squared plus b squared equals c squared, we know the hypotenuse would be square root of 5. So our job is to not really finding out what theta is, but finding sine of that theta, sine of that unknown angle. Well, that unknown angle is this triangle right here. So the final answer is really, well, sine of some unknown angle is going to be opposite over hypotenuse, which is really 1 over square root of 5, which we do need to rationalize. So it's going to be rad 5 all over, or rad 5 over 5, and box that up. Similarly to B and C, find the exact value of cosine composed with sine inverse of a negative 1/3. Well, again, we want to do the inner component first. So we know sine inverse of a negative 1/3 is some unknown angle. We don't even know what that is. So, and we don't care because that's not where we're stopping. But you do want to draw out your triangle. This is when the restriction is going to be important. Sine inverse is restricted in quads 1 and 4. Now it's a negative 1/3, so we want to draw a triangle in quadrant number 4. Here's some unknown theta. We don't know. We don't care right now. We just need to draw out a triangle. Well, sine is going to be opposite, which is going to be negative 1 over hypotenuse, which is 3. Now, the hypotenuse can't be negative, so that's why, as you can see, I'm assigning the negative with the y value, which is negative 1. Using Pythagorean theorem, again, we want to find the adjacent leg. And the adjacent leg would be square root of 8, which you want to simplify down to rad 2. Well, that's not our end goal. Our end goal is really to cosine of that unknown angle. Well, cosine is adjacent over hypotenuse, so our final answer is really 2 rad 2 divided by 3, and box that up. Last part of example 1. Similarly, we want to find tangent of cosine inverse of a negative 1/3. And again, just like the other one, we know this is some unknown angle. Draw a triangle. Think about the restriction of cosine inverse. Cosine inverse is restricted to 1 and 2. Now, because it's negative, we know it has to be in quadrant number 2. Cosine is going to be adjacent over hypotenuse. This is very similar to the other one that we just finished. So the y value would be 2 rad 2 using Pythagorean theorem. Well, tangent of some unknown angle, whatever this unknown angle is, right? Tangent of tangent of that unknown angle is going to be opposite over adjacent. Opposite is 2 rad 2 over adjacent is -1. So our final answer for this question is really -2 rad 2. Example number 1. Okay, pre-calc. Here is our recording for graphing cosecant and finding its inverse. So let's start with a parent function, which is a table. So let me move over here. Now with cosecant, what you want to do is you might want to start with sine value. Oh, that's a bell at the end of 5th period. Okay, so you want to start out with the sine value and then maybe just do the reciprocal because that's exactly the same thing. Okay, so here we go. Sine of 0 is 0, but in cosecant world, it's going to be undefined. So sine of pi over 2 is 1. With cosecant, it's also 1. Sine of pi is going to be 0. Sine of pi is 0, so the reciprocal is going to be undefined. 3 pi over 2, sine 3 pi over 2 is going to be -1, so cosecant is also -1. Sine of 2 pi is back at 0, so that means cosecant is going to be 0. So what is happening is I'm going to do a period to the left and a period to the right. And I'm going to have a few asymptotes, as you can see, starting at 0. Okay, and then there's another asymptote at pi and 2 pi, and similarly to the negative period. Okay, so if you remember, cosecant and secant are going to have u's. So these are going to be parabolas opening up in that way, and down here parabolas opening down, and that means this is now repeating. So this is going to be opening down and this is going to be opening up. Okay, so that's the regular function for graphing cosecant. Now, as you can see, cosecant is not a one-to-one, okay? Because the answer is no, we have to restrict its domain so you can be a one-to-one function. Now, the whole purpose of restricting its domain, so that way when you find its inverse, the inverse is also a one-to-one. Next, we have to decide on where you're going to cut this off. So I'm going to highlight a couple of things. It may not be true at first, okay? So just kind of listen. So what if I were to restrict it from 0 to pi? Well, that's not a one-to-one. That's not going to work, right? So unhighlight that. What if I want to say 0 all the way to 2 pi? Well, that's definitely not a one-to-one. So unhighlight that. What if I want to go negative pi to 0? Well, that's not a one-to-one because this piece is not a one-to-one, right? So definitely unhighlight that. Okay. Then what you want to do is from here to here. Oops, why did I erase that? So what we're going to highlight is this right here. A little bit of that and a little bit of this, right? So what we are really taking is this piece, okay? And what we're really taking is this piece right here, that piece. So those are the pieces that we are going to take, okay? Including this and including this. So as you can see, there's an asymptote in the middle, okay? Which we have to take into account. So restrict its domain, we can write this multiple ways. We can say, well, inclusive from pi over 2 to pi over 2, but definitely never ever be 0, right? Or we can write it in interval notation because that's a little bit better. It's going to be from negative pi over 2, take a break at 0, union that with 0 to pi over 2 inclusive at the end. I like this way better because it looks like it's more connected, okay? So now let's go and find the inverse. The inverse by definition is really just switching y and x. So x equals cosecant of y, which, because we have to solve for y, that's why we're now going to compose both sides by cosecant inverse, which by definition, cosecant inverse, the inverse notation is really using this symbol right here. So that's my cosecant inverse. Let's state the domain for cosecant inverse and the range of cosecant inverse, okay? The domain of cosecant inverse is where you want to go and look at the range, okay? So the range of cosecant is from negative infinity, take a break at 1, right, of -1, and then from 1 all the way to infinity. So that's your domain. So negative infinity all the way to 1, negative 1, I'm sorry, take a break. Union that with 1 to infinity. That domain of the cosecant inverse comes from the range of your regular cosecant. Now, the range of cosecant inverse is where you have to look at our restriction, where we cut it off. So that's going to be negative pi over 2 all the way to 0. Union that with 0 to positive pi over 2 and inclusive. Don't forget the comma right there, okay? Yes, it's just like sine and cosine and tangent. The domain and range, super important, right? When we're trying to find the exact value. So now let's put these together on the same coordinate plane to see what it looks like. So first I'm going to graph normal function first, restricted, okay? I'm just going to go as far as pi over 2. Pi over 2, negative pi over 2, up pi over 2, and negative pi over 2. That means 1 is 2/3 of the way. So this is about 1, okay? 1, 1, negative 1, negative 1. That means pi over 4 is max center. I don't need pi over 4 that much, but might as well write it. Okay, so this is pi over 4. Pi over 4. Okay, so here we go. I will start out with an asymptote for my regular function. Okay, so here's an asymptote. And all I'm doing is really copying this right here. You see that? So, as you can see, at pi over 2, cosecant is going to be 1. So make a dot at 1 right there. And I'm going to head towards the asymptote. So close dot. And at negative pi over 2, I'm going to make a dot at negative 1. And again, head towards my asymptote. So this green piece right here is y equals cosecant of x, normal with restricted domain. Now I'm going to use red to do the inverse. Let me label the points for you. This is pi over 2, comma 1. This is negative pi over 2, comma negative 1. Okay. So the inverse, if you had a vertical asymptote before, now it becomes a horizontal asymptote. Okay. Now again, I'm doing red. F inverse of x equals cosecant inverse of x is the red piece. This point used to be pi over 2, comma 1, so now it's going to be 1, comma pi over 2, which is that piece. And remember, you're going to be heading towards your asymptote, so go that way with an arrow. Then the other piece, it used to be negative pi over 2, comma negative 1, so now I'm going to go negative 1 and negative pi over 2, and again, head towards your asymptote. So as you can see, hopefully, if I were to graph this out perfectly, it should be symmetrical about this line, right? And this line is called y equal to 2x. Okay, so kind of pinching this in, okay? What I did was, this is the normal, right? This red piece, and that's where we got that's on the bottom, and then the red is your cosecant inverse, okay? And again, always check to see if it's symmetrical about the line y equals x. And this is, I believe, the end of cosecant inverse. Okay, class, this is a recording for graphing secant inverse. Alex wants to say hi. Alex, say hi.
Hi.
That's lame.
Hola.
All right, here we go. We're going to start with graphing regular secant first. So what I normally do is I make a T chart. Okay, so this is your input, which is x, and this is your y, which is your output. Now secant, I want to think of it as cosine. So I'm going to do value for cosine and then do its reciprocal. Cosine of 0 is 0. No, I lied. Cosine of 0 is 1. The reciprocal of 1 is still 1. Okay, so cosine of 0 is 1. Reciprocal of cosine, which is secant, is still 1. Cosine of pi over 2, which is 0. So secant is going to be undefined. Cosine of pi is negative 1. So reciprocal is still negative 1. 3 pi over 2. Cosine 3 pi over 2 is 0. So reciprocal is undefined. And your last input is going to be cosine of 2 pi, which is 1, and reciprocal is 1. Okay. So remember, secant is the reciprocal of cosine. So if you know the values for cosine, you're going to be okay. So I'm going to go 2 pi here to the right and negative 2 pi to the left. I will make each period an even interval. So each tick mark is worth a pi over 2. Then I go up 1, down 1. And I'm going to start with the asymptote, okay, which is a pi over 2. And then 3 pi over 2. That means all odd multiples of pi over 2, you had an asymptote. All right. Now, at 0, I'm going to make a dot at 1. But I know that secant and cosecants have parabolas. Okay, opening that way. So this one, I'm going to go that piece over here, opening down, that piece over here. There you go. So as you can see, this is not a one-to-one because it's not going to pass your horizontal line test. And if you don't have a graph, then you can say, that, I'm trying to, ooh, I did it, I think. Sorry, I'm testing out something. If you don't have a graph, then you can say that, hey, look at this right here, right? You have one y value, but you have two x locations. So that's another reason that it's not a one-to-one. Okay, so one-to-one means it doesn't pass the horizontal line test, or one input can only have one output. Okay, part 1, it's y equals secant of x in 1-to-1. The answer is no. Because your answer is no, we have to restrict its domain. Okay, so as you can see, if I restrict it from negative pi over 2 to pi over 2, it's not a one-to-one. So reject that idea. I'm going to restrict it from 0 to pi. That's better, right? Because this is half of a parabola, and then this is the other half, but it opens the other way. So as you can see right now, that's definitely one-to-one. So we need to restrict it so it can be 1-to-1. Well, we're going to restrict it inclusive, 0 all the way to pi. But as you can see, there's an asymptote in the middle, so x can never ever be pi over 2. Now another way of writing that is interval notation. 0 to pi over 2, take a break, pi over 2, all the way to pi. So let's go and define the inverse of secant. Now the inverse of secant, we're going to start with switching x and y. So x equals secant of y. By definition, I have to solve for y, so now I'm going to compose both sides by secant inverse. So that means secant inverse of x equals y, which is really notation for inverse is f to the negative 1 power. We are now going to state the domain and range of secant inverse, and then we're going to talk about the quadrants. Okay. All right, so the domain of secant inverse, you have to look at the range of your regular, okay? So the range of the regular is from negative infinity to negative 1. So negative infinity to negative 1. Union that with, as you can see, 1 to infinity. So union that with, sorry, the 1 has to be inclusive. Inclusive. So 1 to infinity. That's your domain of your inverse. Now the range is the part that we restricted, right? So this is the restriction. That means that's where the range is going to be. So 0 inclusive to non-inclusive pi over 2, because that's what the asymptote was. And then from pi over 2 to pi. Now earlier we talked about quadrants, okay? Pi over 2, so 0 is right here, pi over 2 is right here, and pi is right here. So as you can see, secant, it's in quad 1 and quad 2. Okay, super important that we go and identify these quadrants. Which reminds me, I forgot to tell you about the quadrant at cosecant. So can you go back up to the notes and fill in the quadrants? Quadrants for cosecant, we talked about positive pi over 2 and negative pi over 2. So quadrants for cosecant is 1 and 4. Okay, 1 and 4. So cosecant 1 and 4, because cosecant is reciprocal of sine and secant is reciprocal of cosine, so they have the same restriction quadrants. All right, so now let's go and just graph the inverse and the restricted part on this graph to see if it's symmetrical. About beautiful line right here called y equals x, y'all. Okay, so I'm gonna go and label these y's, okay, as pi. Now 1 unit is 1/3 of its distance, okay? So, because that's pi is about 3.14. So here's 1, here's 1, here's pi over 2, here's pi over 2. Okay, I'm gonna start with an asymptote. I'm going to graph y equals secant in red, and then I'll do another color for its inverse. So I have pi over 2 asymptote, and 1 right there, negative 1's on the bottom, make that dot. So here's my regular secant restricted, okay, from 0 to pi. And then I'm gonna go in and use rainbow. How about that? Y, oh, it's frozen. Y equals secant inverse of x. So what I'm going to do is I'm going to switch the points, okay? Let me label the points for you, it's easier. 0, comma, 1 is that one. So now 1, comma 0 is my mark. Notice how this curve right here is hugging the y-axis. So its inverse, I'm going to need to be hugging the x-axis, okay? At the same time, I should go in and mark my asymptote for the inverse. So I'm hugging the x-axis. I'm going to be creeping towards the asymptote. Now the other one, this dot right here is pi comma negative 1. So I'm going to go and do negative 1 comma pi for its asymptote. So negative 1 of pi. There you go. Okay. So again, I need to, this curve right here is going towards negative x. Okay. That means I'm going to, negative y, my bad. That curve right is going towards negative y, okay? That means on my inverse, I need to be approaching negative x that way. So check it out. It totally is reflected over the line y equals x, right? This piece is reflecting with that piece, and then this piece is reflecting with that piece. Our final function in the inverse of trig is going to be the cotangent. Similarly to the other ones, let's start graphing out the regular cotangent first, so you guys have an idea of what the regular one looks like. Just like tangent, cotangent also has a period of just 1 pi. So we are going to graph 1 period to the right and 1 period to the left. And each period, we are going to break this down to 4 equal parts, okay? So we're going to go same thing over here, negative pi over 2, negative pi over 4, and negative 3 pi over 4. Now I do expect you to know the main values, x and y, of a function such as cotangent. All of the trig functions, I do want you to know really well what the main values are. So whenever we need to graph, you can bust that out pretty quickly. So for this particular example, I will work this out with you. Well, cotangent, as you know already, it's going to be y divided by x, which is the reciprocal of tangent. Tangent is y divided by, cotangent is x divided by y, which is the reciprocal of tangent, which is y divided by x. So when x is 0 radians, it's going to give us an undefined value, because at 0, x is 1 and y is 0. 1 divided by 0, that's not possible. Then we're just going to pick out the key values, pi over 4, pi over 2. I'm going to extend this line a little bit. Then we're going to go 3 pi over 4, and our last value will be pi. So at pi over 4, I love pi over 4. I love pi over 4 for all trig functions, because, you know, cosine and sine will be exactly the same, and then cotangent and tangent will be exactly the same, and cosecant and secant will be exactly the same. That's why I love multiple pi over 4. Now pi over 2, cotangent is going to be 0, because 0 divided by 1 is going to be 0. Then it's going to be negative 1, and then we're back to undefined. So we have 2 undefined values here. I'm just going to use those as my tick marks. Pi, we have another pi, we know it's symmetrical, so looks like I'm just going to make asymptotes at every multiple of pi, okay? And pi over 4, I'm going up at 1. Let me make one tick mark up here and one tick mark down here. So pi over 4 is 1, pi over 2 is 0, and 3 pi over 4 is negative 1. So it will look just like this. And if you have that one graph, we can just repeat ourselves because trig is periodic. That means it keeps repeating itself. Okay. All right, so here's what a regular cotangent function looks like over two full periods. Now, cotangent is definitely not one-to-one because, as you can see, it does not pass my horizontal line test because we said, no, we have to make it one-to-one functions. Otherwise, its inverse won't be a function. So universally, as you can see, technically, I can pick from negative pi to 0, but most people have decided to pick from this right here, 0 to pi. So we're going to go non-inclusive 0 to pi. And the reason, as you can see, non-inclusive because we have asymptotes at 0 and at pi. So now let's move on to the definition of cotangent. Similarly, right, we will define the definition of a cotangent inverse using the regular y equals cotangent of x. Now, its inverse, all we do is really switching x for y and y for x. So technically, that's your inverse function. But we don't like to have a lot of x equals, so we go in and compose both sides with cotangent inverse to solve for y. And when we do that, we now have cotangent inverse of x. This is your equation for cotangent inverse. Let's define the domain of the domain of cotangent inverse and the range of cotangent inverse, which is the inverse function here. So the domain, let's look up really quickly. The domain is really the range, right? And the range of the regular is all real. So this is going to be from negative infinity to infinity, aka all reals. The range of your cotangent inverse is where we restricted it, which is from 0 to pi. So that's what we will copy down. And you need to know, you do need to know these details. What? I can't move. What the heck? You will need to know all of these information. So again, we talked about the range of cotangent inverse. We restricted it from 0 to pi. Let's connect that really quickly to the quadrants. Here's 0, here's pi. So as you know, it's in quads 1 and quad 2. Now let's recap, right? Review, recap. We only have restrictions between quads 1 and 2 or 1 and 4. So quads 1 and 2, we have what? Cosine inverse, yep. Okay, what else do we have? Division 1 and 2, we have cosine inverse. Okay, cotangent inverse, you're right. Anything else you can remember? Did you say secant inverse? Yes, you did. Now we have quads 1 and 4. Then we have sine inverse, right? Then we have tangent inverse, and then we have cosecant inverse. So as you can see right now, there are 3 in each. Let's quickly graph out our method number 1 here. Graph out our cotangent inverse. And so just like before, all I'm going to do is copy the original and then switch the points. So here's 0 to pi, negative pi, pi, negative pi, and I'm going to divide these in 4 parts. Okay. Next, I need to find my 1 value. 1 pi is about 3.14, so 1 is like a third of its distance. So here's 1. You can eyeball your 1 and negative 1 values here. Okay. Next, I'm going to go up and check out my cotangent. I have asymptote at 0 and pi. So I'm just going to sketch out my original first. Asymptote at 0 and asymptote at pi. At pi over 4, it was 1. And at pi over 2 was 0. 3 pi over 4 was negative 1. So here is my original. I'm going to label y equals cotangent of x. Then I'm going to pick a different pen. And next, I'm going to do my asymptotes. Oh, don't want that one. How about this one? Asymptote at pi, asymptote at 0. Then switching the point, the original had pi over 4 comma 1. Now I'm going to go 1 comma pi over 4, just right there. Then the original had pi over 2 comma 0, so 0, I'm going to go up to pi over 2. The original had 3 pi over 4 comma negative 1. I'm going to go negative 1, go up to 3 pi over 4. And I'm going to be hugging this direction. And remember, we talked about in the perfect world, if I can graph it perfectly, right, it should be symmetric about this identity line called y equals x. It's almost, okay? Now, next, we want to see method number 2, guys. We are also proving or graphing out cotangent inverse using tangent inverse. Now, method number 2 is quite important, especially when we get to second semester and studying calculus. So tangent inverse, if you guys remember, we had an asymptote at negative pi over 2 and an asymptote at a positive pi over 2. I'm graphing out tangent inverse right now. Now, if you don't remember, you can always go back up to your notes and look at it again. I'm going to make a tick mark for pi over 4, and here's a negative pi over 4. So tangent inverse, 0 was 0, right? And tangent inverse, we had a point at 1 comma pi over 4. Let me make a tick mark for pi over 2 here, pi over 2 here. Well, 1, it's like, pi over 2, we talked about this before, it's approximately about 1.5. So 1 comma pi over 4, it's right there. And we also have, this is negative pi over 2 over here on the left side. And we also had a negative 1 comma negative pi over 4. So I just want to make a quick sketch of tangent inverse. Okay. So y equals tangent inverse. Perfect. So oops, I forgot tangent inverse. Now, look at our cotangent inverse that we just graphed. Would you agree that in addition to it being shifting up, it also looks like it's a reflection of some kind? So what if I reflect, I take our tangent, I'm going to pinch it in so you can see both graphs at the same time. We're going to take our tangent inverse and we will reflect it about the y-axis, or actually, because tangent is an odd function, reflecting about the x-axis is the same exact thing as reflecting about the y-axis. So we can go, okay, well, y equals negative tangent inverse of x will give us, I will sketch it out. This is a reflection about the x-axis. So what that means is whatever's on the top is now on the bottom, and whatever's on the bottom, if it's now on the top. So this is what that will look like. Okay? Which is now, as you can see, it's looking like it's going the right way. Now, graph number 3 is I want to shift it up a little bit. Now, tangent inverse has a inflection point at 0, 0. Cotangent inverse, as you can see this point right here, that point is 0 comma pi. So if all we got to do is shift it up by is that a 0? No, not a 0 pi, 0 pi over 2, my bad. Shift it up by pi over 2. Moving it up vertically, meaning that we're adding it to the end. So now if we move it up by pi over 2, so move it all the way up here, this is now my center. And that means I'm going to add an asymptote here at pi and a second asymptote here at the bottom. Remember, we're moving everything up. So technically, everything is going to be all right. Okay, so here we go. This is a sketch, okay? There. So if we shift it up for about pi over 2, then we now have a complete graph of y equals to cotangent inverse of x. So look, this right here And this, after two transformations, they're identical. So method number 2, super important by the way, which I'm going to need you to now write down. Okay, cotangent inverse of x is the same exact as, I'm going to move the pi over 2 in the front because it's prettier. Take away tangent inverse of x. Box this up, and I want you to highlight it. I want you to write memorize, because later I will ask you how to use that equation.